Hi, Alyssa. In case you're checking, pause this because these are the evens. We already went through some of them and we're on number, I don't know, the one after 16. But here are the answers for the first ones, and now we're to number 28. All right, kiddos. Negative 30. Did you put it in the right place? Oh, we didn't finish on this one, did we? Sorry. So one option, adding 2 pi, would have been 8 pi over 3. You could have subtracted 2 pi. What's something else you could have done? Maybe add 4 pi, maybe subtract 4 pi, add 6 pi, subtract. Man, you could have had all kinds of fun. Oh. Number next one, same dealio. You could have added 2 pi and gotten negative pi over 4. If you guys notice, they were trying to get one positive and one negative, but you could have theoretically gotten them different ways, right? But you could have added 2 pi, it still was negative, so they added another 2 pi, which meant adding 4 pi to the original, or you could have added 2 pi to that one. Are we doing all right on coterminals? Okay. Okay? Ish? Okay. All right, so negative 30 is going to be in the fourth quadrant because it's down a little bit, right? Negative 750, that was rough. How do you guys think about this one? Yeah, take away 360, that's a good idea. What would that be? A was negative 30. Were you going to radians or were you just drawing them?
We were just sketching.
Yeah, you were just sketching.
For 750, I just took it like negative 775.
No, you can't do negative 75.
It was negative 135 for A.
So it's like a misprint, you guys think?
Yeah.
Okay, hold on. Oh yeah, they said the wrong angle. That's weird. Okay. So then negative 135 would have been in what quadrant?
No.
Yeah, it would have been in quadrant 3, right? So negative 135, you go 90 and then 45 more. I apologize for the typo. You guys know what happens, right? Struggle. Okay, but the number next one was right? Number 7 or 750 degrees. Okay. How did you think about that one?
360.
Yeah, how many 360s are in 750, right? So you have to go negative, so you have to start, and you can see them starting right here, but oh my goodness, they went all the way around because negative 750 means negative 360 plus negative 360 plus, oh, there's more? Negative 30. So you go one whole revolution, go another whole revolution, and then go 30 more. How could you figure that out? I guess you could have just subtracted 360 from 750. You wouldn't have wanted to subtract it from negative. That would have made it messy. Or you could have added 360. Either way. That's 360, that's 720, and there was another 30 in there. Does that kind of make sense? You have something greater than 360. Take away the 360s and see what's left. Okay, number next one. Complement of A, 44. Supplement of A, 134. Oh my goodness, were they degrees? Letter B, complement. Why not? So you can't have a positive angle to add to it to make 90. So no complement. Supplement, just subtract 87 degrees. Uh-oh, are they wrong again? Oh, look, you're killing me. Okay, number 32 is 46 and 93. Was either of them right? Okay. Nicole, you're right. You can grab it from me on the way out. But 46 was right? Wait, 32 is right. 46 and 93? There you go. Okay. Number 38. What were you guys doing? Converting to degrees, right? So we multiply by the degrees are on top, the pi radians are on bottom, and you end up with negative 1.5. Letter B. Still radians to degrees. Is it off again? No, we're okay. Negative 420. Number 44. 337.5. Ew, was an ugly one. What would you have had for fractions? Did you guys keep it in fractions, or did you go to decimals? Oh, it said decimals? Okay, just go decimals. Number 52. Uh-oh, did things start getting weird right about here? Maybe 52 wasn't bad. What was 52's directions? You guys have it right there, right? Ooh, find arc length. Question. Yes, Trey. In our notes. Kiddos.
It changed 152 radians.
That's what?
Don't you change 150 to radians?
Yes. Hold on. Sorry. I was just trying to say we're not quite to these problems yet because arc length was one of the last things we talked about yesterday. Sorry. And so for arc length, remember, you have to change the angle to radians. Now question, how did they change the angle to radians? Do you see it? They plugged in and changed all at the same time. Is that changing? Right here. So they're changing the 150 into radians and then plugging in, Chubby. Although, why is there a 3?
Yeah.
Did you guys write the givens? It was 9 feet, right?
No, actually.
Oh, it was 3? Okay, so that's the typo. Goodness gracious, crazy people. So, r is equal to 3 feet, so that 3 was right, and then you plug in Chuck. Well, that was kind of cool. Anyway. Then you simplify and you end up with, you have the nice little fraction that's perfect, or the nice little decimal that's not so perfect, but it's okay. Although I like 3 decimal places better. Okay, so number 52, that was still using the same formula, true? But somewhere around here things got weird. Number 76 was the last one. You guys had some other weird stuff, right? What were the odds in between 52 and 76?
55, 57, 63, 69.
Uh-oh. So this is maybe where it got a little bit weird because when you were trying to find the central angle, let's go ahead and go back to our notes for a second then. We did talk about arc length. Central angle, actually, did they give you arc length in number 53? Did you guys have 53 or 54? Well, that was taking us a whole minute just to decide whether or not we had a problem. All right, I'll go look. You're at 55. Okay. Oh my goodness. Wait a minute, kiddos. Were you able to do 55 also? Arc length and radius to find radians. Okay, that one's okay. All right, here's where it got weird, right? Which would have been right for these last 4 problems. All right, kiddos, let's go ahead and talk about these notes then. In homework, we are up to the place where it got weird. In number 57 and beyond. So let's go ahead and talk about these formulas quickly and then we'll go back to see if you guys had any questions on those last 4 problems.
Yeah, I thought it was in the world.
Okay, give me that. Yeah, let's do Wednesday. Okay, linear speed. Question. Is there another way of writing this formula because we have something for arc length? Not literally. In your notes.
Oh.
Yeah, what does S equal?
R.
Yeah, the beta thingy. So we could theoretically have another way of writing this formula, right? T stands for time, S stands for arc length. Arc length we could get from radius and, radius and then the angle in radians. So remember, always have to keep them in radians for these types of formulas. Central angle, what do you think I wanted in degrees or radians? So quick reminder. Okay, anything else? Area of a sector, what do you think I want this in? Okay, that's all you need for these formulas. Let's keep going. Degrees, minutes, seconds, what's going on there? Really quickly. 1 degree is a pretty good measurement because it's pretty teeny tiny, right? Why on earth would you want a partial degree then? Why on earth would we maybe want to talk about a half degree? One is, but why more specific? One is so tiny. We saw it yesterday, right? Isn't one super tiny? Relative to the size of what?
Of the arc length.
Of the length of the angle, which might be similar to the arc length of. So Question. If you were to take, let's say, the entire Earth, and if you were to say, go to the North Pole, and think about 1 degree starting from, let's say, International Timeline. Sure, why not? So you turn and you face the International Timeline, whatever that. Which one? Latitude? Longitude? Longitude. Good. Longitude goes long and latitude is like a ladder. Anyway. The prime meridian? Wherever. Okay, so you're facing, and then you turn 1 degree. Now, have you turned very far? If you started on 1 and went 1 degree? No. But what if that 1 degree now maps down the entire world to the equator? Wouldn't that be 1/360th of the entire width, the entire circumference of the Earth? How big is that? It's a lot bigger than the little 1 degree on your little protractor when you're standing on the North Pole, right? Okay, so could we maybe, depending on what the 1 degree is measuring, could we maybe want to split that into smaller sections?
Sure, yeah.
Green in your face right now. Anyway, yes, you might want to. If you were lost in the middle of the ocean, you would want someone to know precisely where you are and not just, I don't know, the nearest degree. Maybe the nearest degree would help. But they had a specific latitude, longitude with specific measurements, they could find you exactly, not just, they're in this part somewhere. Anyway, so there is a way of splitting a degree down into minutes and into, well, every minute can be split into seconds. Now, why do you think it's called minutes and seconds if it's actually talking about partial degrees? Yeah, right? It's 60. We're splitting a degree into 60 pieces and splitting a minute into 60 pieces. We can call it minutes and seconds because it's like the 60s of 60 seconds in a minute, 60 minutes in an hour, but we're using them to split up degrees. Yeah, that's kind of the conversion-ish sort of thing. So if we had 13 degrees, 2 minutes, 10 seconds, which is much more precise than the decimal you're about to see. That might need to be rounded, and then if you round the decimal, you're not very precise, you don't know exactly where they are. How would we think about this as a decimal? Well, we have to say you have 13 whole degrees plus, how do we get the minutes and the seconds into degrees then? If we know this little conversion, some of you are just logically saying divide by 60 and you're totally right, but the reason why is because we do 1 degree is 60 minutes. We're building a bridge again. And what happens to the minutes? And how much of a degree do we have? 2 over 60 is 1 over 30, right? So we're going to add 1 over 30 plus, now who do we need to convert? The 10 seconds, right? So you can divide 10 by 3600. Why what? Because, well, the way it's been split up is into 60ths, and I think just the minutes and seconds came from, 60ths, let's just call them minutes and seconds, because that's how we split up hours and time. So then how can we convert to decimals? Plug in, John. Someone, calculator, you have it close, right? What's 13 plus 1 over 30 plus 10 over 3600ths? What looked really nice with numbers a second ago, 13 degrees, 2 minutes, 10 seconds, is now going to look a little bit messy. This one, the whole string. So 13 plus 1 over 30 plus 10 over 3600 as a decimal. Which one's more precise, that one or that one? The right one we can think of more, right? Because it's like, I know exactly, or I know it's 13 and a little bit. But doesn't this one, don't you have to round somewhere? This one's a bit more precise. seconds. And if instruments are measuring with degrees and minutes seconds, I can be way more precise here as opposed to decimals. How do you measure a decimal? Like the protractor, you can't fit that decimal on the protractor, right? 1 degree is like, so therefore, if we have instruments that measure the minutes and the seconds, then we can get to exactly where we need to go.
Can you explain just the 1/60 that last stuff in?
Remember, if I have minutes already and I want to get to degrees, I can look at basically this equivalency, kind of like we were yesterday with pi equals 180 degrees, how they're the same, or like 5,280 feet are in 1 mile for something else. We can say 1 degree is 60 minutes. So if we have a minutes up top, our bridge, we need to cancel out with minutes on the bottom. So we're going to make the equivalency, we're going to make this statement, but we want the degrees on top so that we end with degrees. We want the minutes on bottom so we can cancel the minutes out.
And then it's the same with the time.
Because this one, I use this one first to cancel out the seconds.
Okay.
See it? And then I cancel out the minutes, and then I have the degrees, and I can put all the degrees together. There we go. This says without calculator, which means it's in our calculator, and some of you might have been looking for it in your calculator. We'll see if you found it. But first, how could we do the math of converting to degrees, minutes, seconds when you have a decimal? How do you go backwards?
326.
Okay, so the 14 degrees, we know that part stays, right? So when you take the 0.326 and Steve, what are we going to do with him? That's in degrees. What if we need to get to minutes? What do we multiply by if we need the minutes on top and we need to cancel out the degrees? So let's multiply by 60 minutes over 1 degree. All right, what do you guys get? Plug and chug. Use your calculator. Yeah, there you go. DMS. Degrees, minutes, seconds. The degrees, they cancel out, right? Because of the little bridge. One more time, question 19 point.
Well, 19.56. It's just.
Do you guys agree?
Yeah.
Okay, and that's even, right? No more decimals? Okay. Now, those are minutes now, right?
3,600?
Let's take out the minutes. We have the 19 minutes, right?
Oh, yeah, because we're ready.
Who's extra? Who's the partial minutes? Okay. So let's take the 0.56 minutes and let's get him more precise. So what are we going to multiply by? He's in minutes already, Lucas, so we don't need to multiply by 3,600. Just multiply by 60. Because now we're going to seconds. You guys see it? We're just multiplying by the little factors from up above, but flip. Now my minutes will cancel with 0.56 times 60. 33 point. And now at this point we're saying, oh, stink, there's nothing else more precise, but for most GPS locations, that's precise. Interesting. Interesting. Okay, so for our little measurement of triangles and whatnot, and angles in, I don't know, real life objects like a house or the angle of a roof or whatever, is it very practical to have degrees, minutes, seconds? Not really, right? Our measurements are of things that are so small it doesn't make a huge difference, but when you're talking about navigation and latitudes and longitudes, if the entire width around or the circumference around the earth is being split into 360, yeah, these distances are a little bit bigger than the degrees of us with our protractor measuring an angle on our paper. So that's why we have these partial degrees called minutes and seconds. Okay, let's sneak back into our homework really quickly because there were a few at the end that I was going to make sure you guys are okay on. It's like these last 4. Isn't that kind of where you guys got to? My ones that worked on it and you diligently got up to where you got stuck? Okay. So number 57, let's peek at him real quick. Oops, I had it open already. Boop. Okay. 57 says, area of a sector. Oh, isn't that just a formula you guys plug and chug? Okay. So new formula you had today, plug and chug. It was from this page right here. You're plugging and chugging. Angle needs to be in radians, but on 57, guess what they gave you? What? Sweet, go team. Remember next one in your homework, 63. I keep on doing this, struggle. Hold on. There we go. 63 Ooh, is that one a little bit of a beast? Okay. Let's go here. Let's go to the end, and let's just talk about these last few just because they're a little bit funny. I could have done some extra examples, but to help you guys on homework, let's just talk about the ones that you have to face. Sound good? So we have 63, and then 69 and 76. So number 63, let's look at them. People who are here, if I were you, I'd get out your spiral, because that way you could just look at them in your spiral. People that have not gotten up to here, maybe instead you should work on them in notes, or just pay attention and then go back and look at notes to get help when you get there. He was not cutting it. Let's do this one instead. I don't like that picture. Let's do one more. Here we go. There he is. Okay. All right, kiddos. We have some new formulas you wrote down in your notes today. Let's talk it through just for a second. Circular blade on a saw rotates at 5,000 revolutions per minute. That sounds like a speed. Find the angular speed of the blade in radians per minute. Hey, if this is already a speed, can't I just say I'm done? Isn't this a how fast? But what's wrong? That one says revolutions and letter A says radians. Well, hold on. Maybe this is just a simple unit conversion. Maybe we don't even need any of those formulas after all. They already gave us the speed. Who do I want to stay? Minutes. Minutes are fine. So I need to somehow get rid of revolutions and somehow get into radians, right? What's a revolution?
So maybe 2 pi because.
Does that make sense? He said a full. How do you get to 2 pi? A full. Oh, what's that in radians? 2 pi. What happens to the revolution? Boop, boop. Got it. 10,000 pi. Sound good? Radians per minute. Done. You guys read B. Isn't there a formula in your notes for linear speed? Let's go find it. Equals, you guys find it? S over T. So R times theta over T. What do we have over here?
We have R. That's the diameter.
Okay, we have R because we have the diameter.
R is half of that.
R is half of that, which would be, that's 3.25, which would be, no, sorry, 7.25, which would be 3.125. My decimal people, you got that right. Or you could say 3 1/8. Is that better? 1/2 or 1/4. But what am I multiplying that by? That's the radius. Those are inches. I need theta over time. I need angles over time. I need radians over time. What did we do in A? They didn't label it, the little stinkers, but what was that? If it was radians over minute, that was talking about theta over t. So without even knowing it, we already figured out what theta over t, wait a minute, hold on, theta over t, how did we figure, oh, they gave us, we found the angular speed, so to find linear speed, all you gotta do is multiply angular speed times, so all you gotta do is take what we just found, which is the 10,000 pi, and multiply it by r, which we just figured out, and so we just need to plug in that whole little 10,000 pi, okay, maybe we wanna go to decimals at this point, but I'll trust you guys can multiply that and check it with the back of the book and be good.
And what's the over T? What's the over minutes, right?
Yeah.
Radians.
So they said angular speed, and we were able to take the speed of the saw in revolutions per minute, change it to angular speed. Angular speed is theta over t according to our formulas. And for linear speed, we just needed to multiply r by what we just had found. Tricky, but not impossible. All right, that was number 63. You guys also had number 69. How bad was he? Maybe some of you didn't get that. Area. What are we talking about? Area of a region, of a partial region through which a sprinkler is rotating. What formula do you guys think that matches up with? Area of a sector, right? Sprinkler is turning. You're trying to figure out an area. For area of a sector, what pieces do you need? Radius and radians. Do we have it in our problem? Oops, that's not the one we want. Go away. We have angle and degrees. What are we going to do? Change it to radians, and we have, what does 15 meters do? Sprinkler in a golf green sprays water over a distance of 15 meters. Here's your little sprinkler, right? And it's going how far? A distance of 15. And then what's it doing? Rotating, right? So it's going out 15 meters and it's rotating around. So therefore the out, look at the circle, what's that going to be? The radius. So they're being all tricky and putting it in context. If you're looking down on the sprinkler, here he is, he's going over 15 and then he's rotating around, right? Assuming he's going in a full circle. It's probably going right. You're welcome. Okay, so do we have the radius? Check. Do we have the angle when you change the radius and plug in? Check, check. So the very last one was number 76. Trombones like the big brain. Good movie. 76. Is a degree or radian the greater unit of measure? One. I wouldn't use that. But you're right that a radian is the bigger measure.
Because 1 radian is like a bigger number than like 180.
Okay, think of it that way. 1 radian, 1 over pi, is a bigger ratio than 1 over 180. That's one way of describing it, right?
Mm-hmm.
So 1 over pi would be like 1/3-ish, and 1 over 180 is. Any other ways? More accurate, because talking about the radius. So it's 1 radius mapped around instead of 1 little 1/80th of a rotation. Something like that. You guys are able to explain. I would have taken either of those. I like the idea of 1 over pi being bigger than 1 over 180. Kind of gets the idea across. Kiddos, let's go ahead and get into section 4.2. Hopefully that helps you. Maybe not all of you have finished homework, but at least you've seen some of those tricky ones. And we have finished our notes for section 4.1. Oh, look, I had the circular saw one ready. Section 4.2. Look at what's here, guys. You missed it? It's back. It's like your favorite number?
Yeah, Parker did not make it right.
Okay, guys, we got this. All together. All for one, one for all. We'll pass through this time. Okay, you ready? What is that before we do it? The purpose of the unit circle is to have quick ratios for sine, cosine, and similarly all the rest, tangent, cosecant, cotangent. For certain particular special angles built upon the 30s, the 60s, the 45s of geometry. In geometry, 30s, 60s, 45s, those were important, right? A 30-60-90 triangle, a 45-45-90 triangle. You guys memorize like ratios of sides? Because they're important reference angles is what we would call them. The unit circle says, let's put together all the different 30s, 60s, 45s, and similarly 0s, 90s, 180s, 360s. In one place and see the pattern of their different sine, cosine, and tangent values, because these are ones that happen frequently in different calculations that we're going to be finding. And all of it technically comes back to just the equation of the circle that we've already seen this year that says Well, this might be a little harder. But you've seen it. X squared plus y squared is r squared. But for a unit circle, think units on a ruler. What would be the units on a ruler? It's 1 inch or 1 centimeter. You're going by 1 inches or 1 centimeters, right? On a yardstick, well, same thing, going by 1 inches. The units in a sense are the tick marks. And anyway, this is called the unit circle. The unit circle. The unit is, we're making it just 1. 1 what? I don't know. 1 inch, 1 yard, 1 mile, 1 centimeter, 1 something. Because the ratios will be the same, whether it's a 1 inch circle or whether it's a 1 mile circle. Ratios will be the same. So we have the equation of the circle, x squared plus y squared equals 1. And the coordinate points for the angles, you guys notice how far over and how far up. If the radius is 1, well, okay, we could say this is 1, but what else could we say is 1? Aren't there lots of different radii for a circle?
Mm-hmm.
Isn't it just from the center to the outside? Couldn't I call that 1? And if that's true, I could actually say, when I say x, I could actually say x over 1. And when I say y, I could say y over 1. And if you guys think back to what you already know of trigonometry, adjacent over hypotenuse and opposite over hypotenuse, these coordinate points that we're going to memorize or we're going to get really good at finding for certain special angles are going to be the same thing as, anybody remember who adjacent over hypotenuse is, that ratio?
Cosine.
Cosine. And what's opposite over adjacent going to be?
So, no, tangent.
Opposite over hypotenuse.
Oh, hypotenuse.
So, and who's your theta? Right there. So we are going to be relating right triangles with ratios of sides to their corresponding angles. They're going to relate to trigonometric ratios. So Patella and Toshikawa. It's coming. It'll be exciting when we get there. Do we have it? So, last year, all of you saw the unit circle, right?
Yes.
What were the parts of it? These, there were ratios, there were x's and y's,
The radius, the degrees.
the angles, and that's it, right? The angles, maybe in degrees, maybe in radians, okay, we should be able to do both, right? The angles, degrees and radians, and the points, and that's it. So we're just trying to memorize certain angles and their special points, their special cosines and sines that go with them. So when we start in on this craziness, in order to get all 6 trig functions, there are a couple things we should probably write down. The nice thing is we've already written down one of them. Sine of, oh, they said t. They're making t be an angle. I said theta. Either way works. If you want, maybe let's go through and make them all thetas. Sine of an angle in the unit circle is going to correspond always with the y. Cosine is going to always correspond with the x. Tangent, since he's opposite over adjacent, is always going to correspond with the y over x. Cosecant is going to be the 1 over y because he's the reciprocal of sine. Secant, 1 over x, he's the reciprocal of cosine. Cotangent, the reciprocal of tangent. So you flip it, flip it, flip it. But this is just quick reminders of who sine, cosine, tangent, cosecant, secant, and cotangent are. And we're going to talk more about these in the future. This is like your first introduction to all 6 of the trig functions this year. And it's just an application to the unit circle of what the unit circle can tell us. If we have the x memorized, sweet, we know the cosine of the angle. If we have the y memorized for a certain point, sweet, we know the sine of the angle. And if we have these two, oh my goodness, we can use them to find the rest. Is that mine? Did I ever turn my sound off? Ding. Okay, coming back. Secant and tangent are undefined when? What's going to make those ones undefined? Denominators of? But hold on, secant and tangent, they both have a denominator of x's. And cosecant and cotangent have denominators of y's. Okay, this homework took a little longer than I thought, but it's because we went a little under yesterday. So, if I were you, finish up 4-1 entirely, and if I were you, find some sort of copy of the unit circle to bring in for tomorrow. Find some sort of copy. Go online, you can print out a picture. Bring it for tomorrow. We're going to talk through it. Get really good at it. But this homework will be due on Friday. Bye, guys. Bye.